Now that we've gone over the slope formula, we need to focus on the distance formula. Unlike slope, the distance formula focuses on the exact measurement between given points, not the rate of change. So to start, let's take a look at what points A and B have. A is at point 1, 1. B is 1, 2, 3, 4 to the right, and is 1, 2, 3, 4, 5 up. So since I went 4 to the right, 5 up, your corner point here is B, 4, 5. Now, to find the distance, we need to take into account the horizontal distance and vertical distance between the 2 points. Meaning, we have to take the measurement between here and here to find out this length. And if you look closely, we have just made a triangle. What we can use in this instance is the Pythagorean theorem. In this case, our distance between here, our y2 minus our y1, could be considered our side A. And for your horizontal side, or your base, the measurements of x2 minus x1 could be considered your leg B, which means our unknown measurement is our C. So let's rewrite it first as the Pythagorean theorem and substitute in what we need to find the missing length. Your Pythagorean theorem is written as a squared plus b squared is equal to c squared. To find c by itself, we need to undo this exponent. To undo your exponent, we have to square root both sides. So we would square root our a squared plus b squared, and we need to square root c squared. This square root, when being placed on top of our c squared, gets rid of the exponent, but we still have to leave the square root on the left side. So your equation should now look like the square root of a squared plus b squared is equal to c. Now that we have our Pythagorean theorem rewritten to what we need, let's substitute in the values we have in the example right to the right. So we said in the picture that A is y2 minus y1. Substitute that in. Have y2 minus y1. Now it is important to note that even though A is this value, we have it squared in our formula, so don't forget to square y2 minus y1. And the same thing goes for side B. Side B is x2 minus x1. So we should have x2 minus x1 squared under our square root. This will give you your missing side. Here is the formula that we will be using for the remainder of this lesson. Let's practice now with the example we've been working on. So again, point A was 1, 1, and B was 4, 5. I'll rewrite it below to start a new workspace. A, 1, 1, B, 4, 5. Now again, just like with slope, I highly recommend that we write our points and label them just like we have in our formula. So x1 would go to 1, and 1 would be our y1. That goes to your point A. It's our first listed point, so it's going to be our x1 and y1. Since we declared B to be our second point, we will say 4 is x2 and 5 is y2. Now that we have our points labeled, plug them into your formula to find the distance. Your length of AB is equal to the square root of y2, which is 5, minus y1, which is 4, squared, plus x2, which is 4, minus x1, which is 1, squared. Before we can move on to using the square root and squaring our values, we have to solve what's in between our parentheses first. So 5 minus 1 gets us 4. Rewrite the equation below and plug in 4 squared. And again, 4 minus 1 is 3. So add 3 squared to the right of your value. At this point, you should have no parentheses remaining in your square root. We're going to be focusing now with squares and square rooting as our operations. 4 squared gets you 16, and 3 squared gets you 9. Rewrite it again below as 16 plus 9. Before we can square root, we have to add these two values together. So 16 plus 9 gets you 25. You have the square root of 25 right here. If you were to plug this into your calculator, your value of the square root of 25 gets you a length of 5. So your length on the graph A to B should be a length of 5. That is your distance. With that in mind, let's get started on the next two graphical examples. We use the distance formula in particular when we can't exactly count between these 2 points. Notice how they're crossing in an uneven way through every single box on this graph. Using that, we can use the distance formula. Again, draw your sides out. That way you can better visualize what this formula is doing for you. So we have a base and a height that we are going to be working with to find our missing length for AB. A trick here is that if you actually take the time to draw this on your graph, you don't even need to find the differences between each point. You can find the length of each side on the graph itself by counting. So instead of doing the subtraction, we're going to go ahead and use the graph for this example. For our base, we have a length of 1, 2, 3, and 4. So since I was able to count 4 for my base, I can say my horizontal length is 4. Same thing goes for your height or your vertical length. I'm going to count 1, 2, 3, 4, 5, 6, 7. With a counted value of 7, that means my height has a length of 7. Now that we have those two values, you can say, and relabel it below, that x2 minus x1 is equal to 4, and y2 minus y1 is equal to 7. Take these two values and plug them into your equation. You should have the square root of 4 squared plus 7 squared. No subtraction needed. We can jump right into solving these. Just like below, when we had in the first example, 4 times 4 is 16. So you should have the square root of 16 plus 7 times 7, which is 49. Now, to find our final value for AB, we have to add these two together. AB is equal to the square root of 16 plus 49, 65. For this example, we will be leaving it as the square root of 65. The reason why I'm doing that is because this will actually not get you a whole number as in example 1. However, if you were to plug this in, you would get a decimal. That is okay. Decimals are okay. Just make sure to round to the nearest hundredth every time. For the next example on the graph, we have one where your slope is actually going into the negatives. So we still are allowed to draw our triangle. Your base can be drawn as such, and your height will look like this. And again, you can either go off of the points and do this algebraically, or you can count and then plug in the value. Let's go ahead and count and plug back in. So for your vertical height, you have 1, 2, 3, 4, 5, 6, 7. So you have another height of 7. For your base has a measurement of 1, 2, 3, 4, 5, 6, 7, 8. So not another whole number again. We can tell that from looking at this, we will not get a nice clean square root. Write out the values just like we did over here. Your x2 minus x1 is equal to 8. And your y2 minus y1 is equal to 7. Plug them into your formula. The length of AB is equal to the square root of 8 squared plus 7 squared. Now 8 squared is equal to 64, and 7 squared is equal to 49. And if I were to add those two together, we would have 64 plus 49 is 113. Again, not a clean square root, so we're going to leave it as such for now. But if you were to plug it in, round your decimal to the nearest hundredth. Which means if you were to round to the nearest hundredth, it would be the second space to the right of your decimal. Let's take a look at some examples where you're not given a graph. In this example, we have to find the distance between the 2 points 0, 0 and -2, -6. So in this case, we actually cannot do any counting, but what we can do is do the original formula that we practiced at the beginning of the lesson. Before we start, label your points. Your first one will be your x1, y1. Your second point listed will be your x2, y2. Now, plug them into the formula and solve for the distance. So your distance, and we're going to mark it as a capital D, is equal to the square root of -6 minus 0, this being your y2 minus y1, squared, plus your x2 minus your x1. So -2 minus 0 squared. Solving algebraically in your parentheses first, you should get an equation of the square root of -6 squared plus -2 squared. Next, we have to square our two values. Even though this is a -6, that is okay. Any negative multiplied by itself will always turn positive. So -6 times -6 gets you a positive value of 36. Same thing goes for -2. -2 times -2 gets you positive 4. And if we were to add those two together, you'll get a distance value of the square root of 40. This can actually be simplified. When we simplify radicals, what we do is we find the largest value within this number that can be pulled out of your square root, meaning that it can be square rooted. So let's try 4 times 10. 4 times 10 still gets you 40, but the 4 can be rooted. Since I could square root the 4, that means I'll have a 2 on the outside. But 10 cannot be square rooted, so you leave it inside of the operation. Both this value and our final value will get you the same answer. But if you want something more clean and a little bit more simplified, I would suggest going as far as you can with it. For the next example, we have to find the distance between points 1 and 3. So x1, y1, and 7, 10, or x2, y2. And again, we plug into our formula now that our points are labeled. So distance d is equal to the square root of 10 minus 3 squared plus 7 minus 1 squared. Solving algebraically in the parentheses, you should have a value of 7 squared plus 6 squared. And again, just like above, we're going to square the 7 and the 6. So under your square root, you should have a value of 7 times 7, which is 49, plus 6 times 6, which is 36. Next, add the two values together. 49 plus 36 is equal to 85. Your final distance answer is the square root of 85. Moving on below, find the distance between the points 3, 6, so x1, y1, and 6, 10, x2, y2. Plug them into your equation. The distance of these 2 points is equal to the square root of y2, which is 10, minus y1, which is 6, squared, plus x2, which is 6, minus x1, which is 3. Your equation should look like this, plugging in the values from the right that we've labeled. Next, we have to solve the parentheses. 10 minus 6 is 4, 4 squared, plus 6 minus 3 should get you 3 squared. And if you were to square those two numbers, you will have 16 plus 9 under your square root. We're not quite done yet. You have to still add these together. You should have the square root of 25. And if you plug that into your calculator, the square root of 25 gives you an answer of 5, just like in example 1. That would be your distance for example 3. And finally, we have example 4. Example 4 has you finding the distance between points 0, 0, x1, y1, and 9, 3, with 9 being your x2 and 3 being your y2. Plug them into your formula one last time. The distance of these two formulas is equal to the square root of y2 minus y1, 3 minus 0 squared, plus x2 minus x1, 9 minus 0 squared. Solving algebraically first, you'll see that you have 3 squared plus 9 squared under your radical. So, next step, square each number and add them together. Under your operation, you should have 9 plus 81. And 9 plus 81 gets you the square root of 90. And much like our first example on this second page, we can actually reduce this further. If I take that even further than we have it, we can do 9 times 10. 9 can be square rooted to give you an answer of 3. Since I can square root 9, I will do so and move it to the outside of my operation as a 3. But 10 cannot be square rooted, so leave it inside. Again, 3 times the square root of 10 gets you the same answer numerically as the square root of 90. It's always just nicer, though, to have it simplified if you need to work with it later on in Algebra 2.